Alright, so I want to show you how this is done. There's two ways to calculate standard deviation that I know of. And your textbook has the harder way. Oops, I didn't mean to erase these numbers. That was 54 and X bar was 5.4. Okay. The textbook has the harder way, and that's the one I want to show you first because the longer, slightly longer, more tedious way of calculating the standard deviation is also the most illustrative of what is calculated. So I'll explain it as I move along here. So I don't know if you want to take notes on what I'm about to do. You might want to save it till when I give the easier computation of standard deviation. So this will be the harder one first. Here's what we do. The mean or the average of the data was 5.4. So I need a column that looks at the difference between the mean and the x's. And so that would be x minus x bar. Or literally x minus 5.4. Alright, so 5 minus 5.4 is negative 0.4. 7 minus 5.4 is 1.6. And we keep doing this. 0.6 minus 2.4. I think, yes. Minus 1.4 minus 0.4. This one is 3.6. And 0.6 and minus 1.4. Okay, so there's our individual variances, I call them. I don't know if there's a technical term I'm not aware of, but I call them the individual variances, are these differences here. Alright, so of course the negatives indicate the numbers that are below the mean, and the positive indicates those that are above the mean. Alright, now, well, what's the average variance here? Well, we could just simply take the average of that list. The problem is, if you take the average of this list, you'll get 0, because the negatives will cancel the positives entirely. And I haven't checked it on this one, but I believe it will. You could check it yourself. That's what I've always seen. Alright, so no good, no good. We need something else. Well, we could take the absolute values of these, just turn them into positives, and take its average. And that is another measurement of dispersion. I don't know what it's called. No one uses it. But the other, actually it turns out the most convenient way to measure this idea of dispersion is to next square these numbers. And so I'm going to take this, the x minus x bar column, and square it. Alright, so we square these. I get 0.16 and let's see, what is that? 2.56, 0.16, 0.36, 5.76, 1.96, and 0.16, 36 squared, 12.96, and 0.36, and 1.96. They all end in sixes, don't they? Okay, so we squared that, each of those in that column. And now I'm going to add these up, and I hope I don't mess up my arithmetic because I don't want to redo this tape. Alright, so, but I do have 10 sixes. So 6, 7, 12, 13, 23, 32, 33, 42, 51, 54. Carry the 5. 5, 7, 8, 13, 25, 26. 26.40. Alright, I sure hope that's correct. Alright. I'm going to just interrupt a minute because I want to save what I've done so far, and I'm going to double check that addition here. I'm back, and I'm happy to report that all this is correct. Okay, so now this is the sum of the x minus x bars quantity squared. Alright, so sigma, parentheses x minus x bar squared, is 26.4. All right, so the square of the standard deviation, for our purposes here, is called s squared. S squared is calculated this way. It's the sum of these individual variances squared, sigma, parentheses, x minus x bar squared, divided by n minus 1. Now you might wonder, well, look, if I divide it by n, in other words, if I divide it by 10, I would have the average of this list of numbers, wouldn't I? And indeed we would. Why am I dividing by n minus 1? Well, I'll tell you about that in a while. We'll have to wait a little bit on that. So bear with me. S squared, the calculation is divided by 1 less than the sample size. All right, now to plug the numbers in, S squared would be 26.4 divided by 10 minus 1, 9. And that would be, what would that be? About 2.93, approximately. Okay. Now this means that the standard deviation, is S, and that's the square root of S squared. So this would be about, so I'm going to take this number with all the decimals so I get the greatest accuracy, and its square root is about 1.71. I tell you what, let me just call it 1.7. All right, how many decimals do you need? Well, depends on what kind of accuracy you're looking for. For what I want to do, 1.7 will suffice. All right, so there we are. We have the standard deviation number of 1.7, and you're going to have to bear with me on this because I do want to tell you what in the world this describes. It describes the measure of dispersion of the data, how wide it is, how spread out it is, but it's pretty hard to relate to right now, isn't it? So you have to give me just a little bit of while on this, and because I want to calculate this an easier way, and then I'll explain what's going on here with this number. So bear with me on that. Anyway, but that's the standard deviation number, about 1.7. Okay, so I'm going to calculate it, like I said, the easier way. I like to show this way because it kind of shows how we're measuring the differences between each piece of data and the mean of the data. It's that measurement of those differences. Some numbers are farther apart from the mean than others, and so there's a sort of a kind of a strange average that we take called the standard deviation that measures this wideness or narrowness of the data. All right, so let me give you the easier calculation. This is not in your textbook, I don't think. And I need to erase all this.